So we were talking of zero. Zero is called the case of thermal equilibrium. And in thermal equilibrium, the system is at a temperature but does not have any external stimulus, any external force, be it optical, be it electrical, be it mechanical. None of the additional external forces are applied. The material is in equilibrium with the nature. That was called thermal equilibrium. So zero stands for thermal equilibrium case. If the transport ladder will be essentially under applied voltage or applied fields or negative fields. In that case, this will be disturbed. And that number will say N. Is that right? So we will say how much N varies or changes from N0. That is what we are really looking for. Initially there was N0 and now at applied force of this is this number changing. And that's what all the derived theory is. To start with expression which I wrote, that is a MC exponential. Maybe I should put a minus and deviate equation what I did. Minus EF by KT and E0 is NG exponential minus EF minus G by KT. Okay, so what I do is I multiply this N0 and E0, and right now for simplicity I show the material is intrinsic. What does that mean? N0 is equal to P0 equal to N. So we say for the intrinsic case, this is N0 equal to N, P0 equal to N, so N0 is N square. If I multiply the two, I get NC and V exponential. What should I get? Minus NC minus V by KT. Is that okay? Exponential term, just multiply by final signs, cancels left. So we get NC and V e to the power EC minus V divided by KT. If you see your band gap, this is your conduction band and this is your valence band, this energy band gap is called EG. This energy band gap between conduction band and valence band when no state exists is called, it has a value Eg, which is essentially Ec minus Ev. So that becomes Nc Nv e to the power minus Eg by So now I am interested in equation. I say Ni square is Nc Nv e to the power minus Eg by Kt, or Ni is Nc Nv under the bracket e to the power minus Eg by Kt. So intrinsic charge concentration for given semiconductor is related to the density of states, both in conduction band and valence band, and also proportional to exponential of G band gap, and also temperature. Now can you think the temperature dependence is coming from two terms here. Which are the two terms? One is Nc Nv as 2 pi m star Kt to the power 3 by 2 into 2 pi m star Kt 3 by 2. If you multiply the T to the power 3 by 2 terms, dependence will come from here, and e to the power minus some constant k by t, something like this. Which means some other constant symbols we can make. So we see now which term will start dominating. Exponential. So please remember that though there is a dependence of line on e to the power by 2 terms, even then this term is going to be dominated mostly by e to the power minus e by 2k term. That is temperature change. So will increase of temperature will increase Ni? It will from the exponential term as well as from e to the power by 2. Increase in temperature increases intrinsic carrier constant. How it is physically looked into? Larger the temperature, excitation is larger for the valence band electrons, and they start vibrating, and as they start vibrating, some of them can get on and can that larger the energy to supply, larger is possibly the. Now the problem is that even if you calculate this one, let's say I take a case P is equal to 150 degrees centigrade, and normal at P is equal to 300, what is the value I can declare? Okay, there is a very interesting thing you can see from here. It was found that it is around 6.95 into 10 to the power 10% C. If I actually substitute the Mn star and Np star values which I gave you. Whereas everyone believes that this value is correct. So where is the discrepancy? Essentially, the Mn star and Np star which we evaluated from the band structure, they are theoretical evaluations. Is that correct? They are taken from the Prof diagram. The theory itself has some limitation in solving the final equations because we are linearizing it. So this, the second part is essentially taken from actual measurement of an intrinsic semiconductor. So we believe that since it is a measured value, it may be taken as a more universal value, but if you calculate, you may not get exactly this 1.5 to 10. Which everyone assumes that is equal to 300 degree as the intrinsic charge. Which material I am talking? I am talking everything but silicon. However, if I increase the temperature to 150 degrees centigrade, this Ni values can go as high as this 4 orders high. That's it. If I increase the material silicon temperature to 150 degrees centigrade, I can get the Ni concentration that is called 14 and above. If I increase further, let's say 200, this may become 460. Now this number is very nice because I yesterday calculated some numbers E or D which normal semiconductors is using. They be of the order of 10 to the power 15 or 16% C. This is the kind of routine we use in all devices. If the device which I am operating now is in a system like a desktop system, you can see if you are really seen it, the whole box becomes heatable and the fan will. Even if you touch it, you will find it much higher. We are cooling it by constant fan and air cooling there. But if it, let's say fan doesn't work, it comes, we have seen it actually. The reason is, at higher temperature, NA may be, they cannot change the ionized bonus. With ionized even at 300, so at 150 also they are ionized, 200 also they are. But Ni will now exceed NA. So what will become to a device? All material become intrinsic. Which means there is no junctions, there are no other functions can be possible. The device starts only having a resistance from this and starts using currents. And because of that, the device finally burns because of I square R loss. So there is a maximum temperature this device can stand up to which circuits probably can operate. And in case your device consumes more power, let's say a power device, then you must do something, okay, lower than 165, 175, lower, such that device is operating at the right level. This is therefore I lectured earlier in my first slide to give across the facts that temperature is becoming more and more worrisome rather than the device performing. Device is failing not because of the semiconductor per se, but because of the thermal process which is excessive now. As I said, what is the kind of temperature fuel we get? Rocket nozzle or sun temperature again. If you don't do anything, device may really go into. So this issue has to be understood that why temperature circuits devices have to be much lower than 150 or 170, so that device keeps operating at least. They will not be operating as good even then, but at least they will be operating at that point. So this fact, though this threw into at times many, please remember the extrinsic material then becomes intrinsic, and then there is no junction factor. Both N and P side become Ni, so there is nothing, no value. This is an issue which I thought I didn't have here, but I thought since I saw these numbers, I thought we should know why we are worried so much about cooling. And I suggested research and checks out how to cool using silicon substrates. On these circuits are made, okay, some circuit below, which is called MEMS, microelectromechanical systems, which may create a microchannels. And in that microchannels, we can do what is called closed circuit liquid hydrogen fuel. They keep it ready. So there is an issue, there is a research going on in many labs, including Intel and IBM. Many of the big companies are spending a hell of money actually see how can we cool. So it's not so much device, it's so much right now what it is temperature. And this one of the, so there are many other issues, but one of the major worries is increase of temperature can cause intrinsic material. This is our worry, which we must attend to when we solve further devices. Is that okay? Electricity was not the part which I was thinking, but I suddenly saw this number. I thought I should tell you this. Okay. Now, if I do this, let's look at from the first expression this of here. I can say, so please remember for PG of silicon is 1.1. Some will slide 1.12, which are calling and which are value I will specify with you. If I say it is 1.1, take it in formula whatever. If I say 1.12, so don't say that is movement. Whatever given is the value. So this is for silicon and this is temperature. And this is 1.43 electron volt for so this will have higher now. The same temperature. Effective mass, in fact, for gallium arsenide is much smaller than effective mass for electrons in silicon. So, which one will have higher line? Silicon, because NC is also higher, EG is smaller, which is called minus EG. So, EG is smaller means larger number. So, typically in gallium arsenide, Ni value is of the order of, exactly I don't remember now. Whereas silicon is how much? 10 to the power 10 plus Cc. So there is 3 orders of higher numbers. So what is the problem in gallium arsenide? Therefore, to really create those many available electrons thermally may become very difficult. And that is why many times gallium arsenide is not preferred in some devices, but it will be preferred in some devices. We'll see why. Okay, so having told this, okay, so now let's look very carefully this first expression, and I rewrite Nc is equal to N0 divided by e to the power minus Ec minus Ef by Okay. In the case of intrinsic, the Fermi level lies where in the case of intrinsic? Within. So we say this EF is actually named ER. Intrinsic Fermi level is not called EFI, it is only called ER, which is intrinsic Fermi level, which will be where 50% probability of electron, 50% will so always to be equal. So 50% point will always occur at 50%. Half the activity will occur at half the energy. So this essentially means that if I move the material now, the Fermi level yesterday, where did it move across an incline? It moved towards conduction. Yesterday we calculated, we showed you the function, and if the electrons are larger, the Fermi function moves about towards the band, conduction band, and therefore larger probability of occurrence of electrons. That's what we said, larger incline. Electrons are larger, they move away. So 1 minus Fe went down because the number of ends are higher, so it becomes smaller, 1 minus Fe is smaller. Now this issue means EF started moving about. I want to correlate, that's what it says, how much I am away from EI. But I don't want to really worry about values of EC and EV. From where I start then measuring my energies with reference to EI. What is EI value typically is Eg by T. So that will calculate not Eg by T. It is somewhere, why it is not because the respective masses of electrons are not same. But assuming very close, it will calculate how far we are away from the midpoint. But let's say EI is the mid gap energy level, how much you are above, or in the case of how much you are below, how much you are below EI. So we want to create a relationship between N0 and Ni in terms of Ni will have the Fermi level here. N0 has a Fermi level here. So we say we correlate EF and EI with N0 and Ni, and if I do so, then I don't need to know NC and D, or I don't remember where to be in CI. Is that clear? So this relation which I am now going to show are called Boltzmann's relations. This is the only relation I am using everywhere in my analysis head. So I am interested to derive what I call Boltzmann's. So let's, since I calculated Z, sorry. So from here, actually, let's look at what. Similarly, NC could be also written as Ni upon e to the power minus SC minus EI by for intrinsic and for. So if I equate them, is that clear? From the intrinsic case and from the doped case. It is for the doped case, it is for intrinsic case. Only difference will be here it will be S, here it will be I, here it is N0, here it is Ni. So if I equate the two, the relationship that I am going to get is Ni e to the power EF minus EI by Is that clear? I calculate NC from the two relations, one for the doped end, the other for intrinsic. NCs are same. Equate the two and you get a relationship between N0 and Ni. That relation, that N0 is Ni exponential EF minus, or can be written in a slightly this form, the initial groups. So what does it tell? Essentially, that as EF moves away from EI positive, EF moves away above EI, this term will increase even at a given temperature. If this term increases, Ni is constant. So So what will happen to N0 will increase. So we say whenever N0 increases, EF moves closer to away from EI and the top. By same logic, we do for NV and one can generalize P0 is NI. What should I write here? Time now EI minus here by Secondly, what is the way? Now do it for NV, equal to 2 NVs for P0 and NI to get this. These two relations is essentially called Boltzmann's relation. What is the importance of Boltzmann relation? It does not need your knowledge of G, it does not need knowledge of where, although they were taken care by me by taking care of NI and ER. So it's not that I am avoiding them, but I have now simplified my solutions. Okay? So these relations actually represent the same, except that they are in a slightly different form, which is what I am going to use very often in calculation. So why I am interested in this? Because given a doping or given the particular position, I should be able to know one or the other because NR given different temperature, I can do the same calculation and I can again find how much is the change in N0 I get. So this way I will be able to evaluate carrier concentration of electrons and holes in entire working type depending on how much will be done or where is the Fermi level and where is the either. Now this issue is very simple and very important for us because this relation is extremely interesting. These are not intrinsic values, these are only normal electron concentration and hole concentration. So now I multiply N0. What will happen if I multiply this? This will become NI square. What will cancel? Please remember, this is minus EF minus EI. So what we do is, since this is N times material, we may say it is EFN, and this we will call EFQ. Is that right? For P type, the Fermi level is defined as EFP, and for N type, we define that as EFN. Is that right? So we now say, since ER is common, the separation if there is a material which has both donors and acceptors. Is that what is my worry now? Because in real life, I will have both donors and acceptors in the same way. So in which case there will be electrons also, there will be holes also. And they will be now governed by Boltzmann's relation. So now we say if I multiply N0 this and if they are same this essentially will be always equal to this. This relation is called law of mass action. Now why this is relevant is very important. NP is N0, P0 is NI square say that what condition I have derived this? Thermal equilibrium, no force applied. So when I apply a force, there will be a term which will actually, let's say electricity, which will multiply this. That is what we are looking for. If I apply some stimulus, it will change the product of N0 P0 from its NI square value, which otherwise is always constant. N0 P0 product is always NI square at all temperatures. Is that correct? This is called law of mass action. Let us say now that if I apply electric field to the material, then this N0 P0 will change and their product may not be NI square, will be modified from NI square. And that how much it modifies is what we are looking for. Because that is what we are looking for. I apply electric field, क्या इलेक्ट्रिक फील्ड कितने कहाँ That exactly is my, and then I am looking for. That's what all the expression I am deriving. Actually, what is my ultimate aim to derive? The current versus voltage, capacitance versus voltage. But only for electrical people, we are only interested in these two. How are they? If we can get these relations for the circuit, I know equivalent of that device. I would correspondingly see I have a current source or a capacitive loss variable with, and I solve normal circuit using network. Either using the theory network, whichever conductance is, either using the Kirchhoff one, either or voltage one. I always solve any circuit. Please remember, Kirchhoff law is universal. So it has no limitations. So whatever circuit you draw, it will always be correctly solved. In analog circuit or digital, we keep saying, oh, I can modify that, I don't want equivalent of this exactly, and to simplify my solution. But Kirchhoff law says, even if you don't simplify anything, any network can be always evaluated from its output to input ratio, or from anywhere to input. So at the end, I am only looking for variable voltage or current equations. My ultimate aim, I or call it J, is a function of B and C as a function. If I can get this, then I can be. This is called modeling. What is it called? Device modeling. So I want to model my device into an equivalent of current or voltage sources or current sources or capacity equivalence, and then I solve it. Is that clear? So at the end, my ultimate aim is only to get so-called equivalent circuit of a device. But to reach there, I am going to how this is reaching. So the 80% of courses will be telling how to reach there, and only 20% will say, oh, it can be used now. Because there are other courses where they will only work on that, so I thought, as I told you, I don't know next time I'm teaching another course. But if I teach further, you will not recognize this or whatever other course. So if actually I'm told I'm not going to teach this, so after I made. In that case, I'll show you that, okay, you are already learned the devices, you are already sent important circuit, you are already learned, then you say, no, we are not involved. अभी तक महिलाओं के ऐसा नहीं हो कि तैयार हो. So I only bring you to the end where next course can be. Okay, so this all statement made. Please remember these relations. If you don't say I don't remember, you must remember. Okay, in my just for the heck of it, in my course, kind of exams I take, I take with my sheet. Quizzes are normally, we do not allow any support from anywhere, including from you. They are asked questions like what is objective, what is drawing figures, what is statements, what is solving also. There is no calculator by hand. So, I would tell you that time to think your question. But in the case of test itself, you will be allowed one A4 size sheet. In you can write down any amount of formula. No figure, no text, no statements. And those sheets you will attach to your answer. Those are actually give marks what the way you are doing. What is the test I am doing there? I am trying to know. You at least know what you should know. So even that is a good test, because at least for that time, some of you open the books or notes, and you go copy the notes. So only thing is, most of it called that sheet which I allow you is called POC sheet. POC is a short form of copying a told letter. So this is not there. Any Xerox, but anything which I see same expression going, both will get zero. And unfortunately for you, some of your seniors are so smart, they actually verify very quickly which one is common from both. You always think, because you also become as smarter. You think you are the smartest here, they are also smarter here, you have become smarter now. So they actually did very fast. Last year, 7 students were taught by my TAs as been copying things. Then they finally succumbed to my pressure. They said, I'll give you 0 round. Then they did a study. So I said, okay, I'll give you some marks. But this, please don't try to copy, because at the end of the day, we are trying to know how much we know. If you don't know anything, it's nothing trying about it. But at least be honest. So let's look at the thing which I am looking for. Okay, now please. May I have your attention? Please. I start with a semiconductor, let's say N-type or P-type. I have a uniform accepted density of A. Let us say at room temperature, all of them are ionized. So as many NAs I give, those many moles are created. And then by technology, by some process, I actually create what I call a barrier layer of silicon dioxide, create a window in that where silicon is exposed, and inside this I put N-type impurities and give a heating to this for driving, push the impurities in, and this becomes and I decide how deep this should go. At this point, this is N, this is P. At this point, what is the doping here? Initially, everywhere there was P. Certain regions I not know. So what should have been at that point where N and P change over? Concentration should be 0. N must get balanced by there. This, where it happens, is called junction. So I have made one junction in P semiconductor, and therefore this is called NP junction or a PN junction. And this is nothing but a diode. This is nothing but a diode. N stands for this, P stands for this. This is essentially what diode is all about. Now here is the issue. This material initially was P-type. If I start putting N-type dopant inside, what will happen? N will create electrons, P has certain holes, so these electrons start recombine. How many holes it can recombine? P. At that area wherever I am pushing, I am not going all of this. Whichever area I am pushing the impurities, N will start first compensating. In what it is? Compensating. So any number of donors I put initially, they will compensate the earlier ones. As they start compensating, that is because of recombination going on. Okay, please take it. So as they start increasing any impurities in, and first it will compensate things there. And then further if I add N, that will become enzyme. Is that clear? So the point, if I exactly add throughout this material all N equal to P, the material will become an enzyme. Because it will cancel it. Now this point is very interesting. Certain number of electrons I am creating because of the donors. That is N-type. Since I was creating donors, thermal process was also going on. I mean, that was not separated is there, and I must keep it. But the interesting part is that it does not happen in case of, let's say I was making an N-type barrier. Use this equation here. N is equal to Now mu n is equal to Nd, all of them are ionized. So the P now, N0 is mu N0. P0 will be how much? Ni square by N0 or Ni square by Nd. Plus and Nd right now, I may not put plus every time because I am assuming all of them are ionized. If not, I will have to find Nd minus Nd plus. How many are there? 2, 1. That's it. So this is slightly neutral to this formula, but assume everyone is aligned. So if I know if NTs are larger, that's why I am inside, what will happen to P0? It will reduce. Let us say given a number, this is 1.5 into 10 to the power 10 square divided by 10 to the power 16 per 50 donors per 10 to the power 16 donors per into this, all are nice 14 electrons free. If I divide this, it becomes 2.25 into 10 to the power 4. So how many holes you have got actually? 10 to the power 4 per cc. Okay. How many electrons you have? 10 to the power 16 electrons per cc. Is that not clear? Intrinsic carrier question, how many N0s will be required? 10 to the power 10 kind of thing. So please don't think this 10 to the power 10 will add to this 10 to the power 4 and making it 10 to the power 10 or some kind of material. This is what law of mass is saying. Both processes will try to go together and adjust the value such that N0, P0 is always Ni square. Is that one clear? Otherwise you say P0 plus Ni, which is 10 to the power 10. It's not true. Holes will always be smaller for N is larger, or for N-type, P-type material, if 10 to the power 16 acceptors are there, the electrons will become 10 to the power 2 times. Okay. This is very crucial in all devices. So do not think that generation recombination process is additional to this. This is part of the next system, and this law of mass exercise it is always irresistible. Is that right? So N0 into P0 is Ni square is always value what condition? Thermal equilibrium. This keep remember thermal equilibrium. We will disturb equilibrium and then see what. But right now, they always this law will always follow. So one can see from here, in the N-type material, you have how many moles? 2.25 10 to the power 4 moles. 10,000 or 20,000 moles. You have 10 to the power 16 electrons per second. Therefore, you say N-type, N0 is much larger than P0, material has become, but there is no zero holes. There are finite holes. These holes are in minority in N. Please remember, what are majority carriers in N-type? Electrons. What are minority carriers? Holes. Now, this issue which I earlier said, it is this minority carrier which actually is the major cause of conflict. Which means very funny. 10 to the power 16 electrons है वो ज़्यादा बात नहीं करेंगे और ये 10 to the power 4 हल्ला करेंगे ऐसा ही minority का भी तो विचार हो रहा है उनके हम लेते हैं आपको नहीं देते So this issue is that this number is so very crucial because the transport efficiency matter, which is essentially called diffusion transport, is essentially governed by minorities. Is that clear? And that will dominate all biological processes. Whereas in the case of MOSFET, the current is always due to majority carriers. And there we say, oh, 10 to the power 16 is important so because 16 happens. So in two devices, this so-called majority minority may vary. Therefore, never say that oh 10 to the power 40 है. I don't know 40 सब कुछ है. And therefore, these numbers are very crucial in all device values. How much majority carriers and how many minority. So many a times, we also give a symbol N sub N0. What does that mean? Electrons in N-type material at thermal equilibrium. What is N0? Symbol I give you. Electron concentration in N-type material at thermal equilibrium is N0. and then I will give another name, whole concentration in N-type material at thermal material. So I will also add additional N or P whenever I actually solve equations. So obviously if I say no, without telling you, there is no this is minority difference. Then P and okay. So to differentiate from majority or I just put another symbol below so that I can say these are majority and minority carriers really. Is that point clear? This issue, please take it seriously because this has happened in real life. Now, another worry for me, system normally, let's say you have both NE and ND in the same material as in this case, electrons will charge, negative charge, goes to positive charge. So are we trying to say that the silicon is N-type though, I touch it, I will be shocked. So there is a charge and I will be there. In reality, it does not. Charge always remains neutral. So charge neutrality is always a standard. Always rules. See, another interesting one feature is law of mass action. I now one by one statement I will. First is law of mass action. N0 P0 is R square. Now I say, if the material has both acceptors and donors, which ones have negative charges? How many kinds of negative charge you have? Electrons plus acceptors. Both have negative charge. And what are the positive charges in that? This relation, the N plus P minus, is always equal to P plus ND, because charge neutrality must go. Net charge must be zero. Otherwise, what I say, you are making chips and suddenly you are starting making chips. Because it reserves people normally of metals to uses. So we do get short from here because yes, but not so much. Many of the silicon chips we use, if we do not use properly, they may actually burn, not because actually charge was goes to you and large current should be burned. This is called electrostatic discharge. This really happens in circuits. But that's another thing. Now, if this is so, I can do something this. Okay, N is equal to ND minus NE. Can I replace P by what? Is that correct? So N is equal to ND minus NE plus R square. Right? I can rewrite this expression. I get N square minus ND minus NE. Into N minus NR square. Just substitute P by NR square by N, because that law that mass action is always valid. This cannot be changed. If I solve this quadratic equation, I make a relationship ND minus N plus minus ND minus N square plus 4 NI square 5. Let us say, for numbers, NDs are much larger than NAs. What kind of unit I am talking? NDs are much larger than NAs. So case we may say, also we may say, for the sake of stability, NDs are much larger than this. If this case occurs, how much is N? This can be neglected in terms of ND square, because ND is much larger than 9. So it becomes ND minus ND square only. ND is smaller than ND, so ND square. ND out. N is neglected, ND plus ND by 2 is ND. So I get. So if the NDs are much larger, the number of electrons are exactly equal to N. But these number goes to exist, energy can still exist, but for practical numerical purposes, one can say N is equal to, let's say N is not very large or something, this may become N minus N. The only thing is N minus N is larger than Ni, this condition is still valid, and in that case, N will become N minus N. This is only true when ND minus NA is larger than Ni. Just neglect Ni and you get this expression. Now this essentially means that as many bonus reports, those many electrons I can create in N by material, it should be sufficiently larger than Ni and larger than the base concentration, and you can say all the electrons are available. This, by similar logic, I can do P, and I can say P will be equal to N minus for P prime, which is for N prime. So the whole concentration is almost equal to the acceptor concentration in case the concentration of acceptors is larger than N as well as Ni. When we say almost all holes will be available to you for transport as many acceptors. So in technology, what do? We actually decide how many impurities are in. That's correct. And if I can control those impurities, then I know I am trying to make a device whose electron and hole concentration is known. That's correct. And once electron hole concentration is known to me, I believe, then I can calculate the transport of this carrier because I know the number and enter the business current I will get. So our aim now is to get how many. So one relation has said that whenever such expression occurs, if NDs or NAs are close, use these expressions. But if NDs are much larger than NAs, even if you know general expression, if the numbers are different, this is 10 to the power 16 and this is 10 to the power 5 or 6 or 8, numerically this will be 8 decimal away. So you need not worry too much because your calculator also cannot worry too much. It will automatically do it. So, but you want theoretically, you should always say this. Okay, this, as I say, is important. One small problem on this thing which I did. I repeat that question which I want to know. I was given any concentration of 10 to the power 15 per cc. I was have T equal to 300 kg Kelvin. Find EF minus ER, or position of Fermi levels. Just for the sake of simplicity, number one I want to do. Okay, if any so much donors are there, 0 is 10 to the power 15 per cc. Why is so? Because actually it is slightly depends on ND minus NA, but I don't know ND is as long as ND is. So I say, okay, as many acceptors I have, all are analyzed and all are different holes. So once I know this, How many electrons will be there? Let's say if P is of P0, so how many will be electron concentration? 2.25 10 to the power 10 divided by 10 to the power 15 or 2.25 10 to the power 5 electrons per cc are available in P-type semiconductors. Is that correct? Which in a way is anyway saying that a P-type material, the whole concentration is much larger than electron concentration. This is a P-type material, which is also giving the numbers about larger holes, fewer electrons. I want to calculate what is the relationship I wrote for this 209? Yes, exponential. What did I write? ER minus EF 5kT. I know this 10 to the power 15, this is 1.5 10 to the power 10 exponential. Let's call right now ER minus EF so is my minus EF 80 ln 1 10 to the power 15 divided by 1.5. How much is EI? Roughly will now see how much EG by 2. How much is EG we assume right now? Let's say EG I assume is 1.1 electron volt. So EG by 2 is 0.55 electron volt. This is essentially EI. Since I know this, I can then evaluate the position of Fermi levels. Where if you look in the band diagram, this is my ER, and where will be Fermi level for many P-type material? If you are going down to somewhere, this will be the Fermi level for P-type material. If this number is larger will be EI minus EF is larger. So where the Fermi level moves, the effect comes closer to the balance. Now the case which is of interest to us many times, if you see increase doping, either in quantum material or P-type. In the case of N-type, we may say this is your EI and this was your EFN. And for N-type, the Fermi level is about intermediate level. To keep increasing donors or in case of P-type increasing acceptance. So Fermi level will start moving towards C or E in either case. At some doping, this may reach conduction band is exactly where the Fermi level happens. When you further look, at least then the Fermi level will move into the conduction. In the case of P-type, the Fermi level for heavily doped N-type P-type will go into the valence. But remember, there is no actual level. What is this level we were saying? It's a coefficient level from which we are measuring from. So the presence of Fermi level in conduction band, valence band, which is odd. Then the statistics which are used, essentially or Fermi derived, may not be valid now. And we derive expression for this code maybe not. If EF crosses C or EF crosses B, the material is said to be degenerated. I repeat, if EFN crosses EC or EFE crosses EV, the material, semiconductor material, is degenerating. Our calculation of PF, Goldman relations are not valid. Don't use Goldman relation if PF is either in C, above C, or below in the case of Electron. Then the equations are different and slightly more complicated equations are required to evaluate the concentrations. Then, so most cases in our circuits or devices, what is the way we do it? Doping is normally does not exceed where the degeneracy occurs, at least the part where transport, at least the part where transport occurs, the concentration of electrons and holes never exceeds so much that EF reaches NC or DV or something. But in reality, they may. Because there are states and I can push further. Every state I can push more electrons or more. But this essentially will not reduce them transport. So why I showed you this? There is a device, okay, we call it, which is heavily doped. One side is heavily doped in kind, other side heavily doped inside. Heavily means such that they cross both easily. These are degenerate junctions. Now in this case, this diode, normal diode, has something like this characteristic. These diodes, there are two ways to in some cases, okay, normal diode is this, they show this kind of characteristic. There is no color, I will tell you. What is this diode? This is called tunnel diode. This is called tunnel diode. So I am not trying to say that there are no devices in which much higher dopings are used. There are these are very interesting. Can you see something interesting in this statistics? Other one. What is this relationship telling me? As I increase B, I increase I. Which law I am following? Ohm's law. Is that correct? What is the resistance, positive or negative? Positive. V by Vi is positive. However, this region, I am increasing V when decreasing I. So V by Vi is minus, so we are getting negative resistance. Is that correct? Positive resistance dissipates power. So the negative resistance must generate. Is that correct? These devices therefore can be used as oscillator generating sinusoids or other waves. Is that correct? Whenever I can operate my tunnel diode in some form, I can actually create tunnel diode oscillators at high frequencies. The phenomena which allows this to happen is called tunneling. Normally, why I am showing you this? Because in normal case, normal diode, this rise in current initially very small and start rising and exponential level and so this is essentially because electrons has to cross certain amount of potential barrier. In the case of tunneling, the barrier is never crossed. What do we do in case of normal? Let's say this is my barrier energy. If I am an electron, so it has to go like this. This is called thermal emission. What is it called? So much thermal energy provided, electrons crosses that barrier and jump. If electrons can find a state on the other side, electrons can come directly without climbing this much energy. Is that clear? This is the phenomenon which is interesting, different from tunneling. There are possibilities that the barrier is something of this kind. Say, electrons, if this width is very small, then electrons can tunnel, or if not, electrons can go here and then go. So there are three possible mechanisms in which case. One is thermal emission, the other is tunneling, which is thermal. This is tunneling. And this can be what? Thermally assisted tunneling. Some energy are there, you can keep tunneling. This is called thermal emission, this is called field emission, this is called thermally assisted field emission. So there are different kinds of transport I am worried about. Is that correct? Normally we will not see this, but we must see to it that in your device, if this occurs, where this occurs, and where this is why I am interested every time all this is because my device should perform the way I wish. It should not start doing something which I don't know. So I must know what possibility it can work. So if I do something, it will not do. So I know in this case it works. These issues are relevant when I start designing a device. I must ensure a device engineer that the circuit will guarantee what device I have made and how it can be done. All the phenomena which I am talking in the same thing for this purpose, because I must know if I make something wrong with my process, it should not behave the way I do. So I must know if the way it can do otherwise. So I would like to know all possibilities and okay, and here. That's it. Okay, stop here.